So let me redraw a representative scatter plot. Here's y, which is the predictor, and x, which is the response. And we're going to imagine that we have a data set that looks something like this. And we're trying to find a straight line which, in a particular mathematical sense, comes as close as possible to all the data points. Now obviously you can't put a straight line through and touch all the points. There's still the randomness in here that moves it off any straight line. But you can come up with a reasonable approximation, which by eye might be this. That could be it's a decent looking approximation. Now, what makes that a good answer? A good intercept and a good slope? Well, it all depends on these errors that we make. At each point, for a given x, we're expecting y to be the value that's on the green line. In this case, it isn't, right? There's this gap. That's called an error in fitting the data. And for every data point, there's an error. Sometimes the error is very small, sometimes it's bigger, sometimes it's positive, sometimes it's negative. So we have all of these discrepancies or lack of fit between each data point and the regression line. So what we want to do is say, let's try to get all these little vertical stubs, the red lines, as small as possible. Now, if we tilt the line, say, closer to this one, we can make that error smaller, but we're going to, for instance, make some of these other errors bigger. So we don't want to try to fit one particular data point. We want to come close to all of them, even though we might not exactly hit any of them. And a way to do that is to say, let's look at every one of the errors and total them up. That will give us a summary of all the errors we make, and we might want to keep that small. And that's almost a good idea. We could take, we could say the error is each y minus each x, and we could add those all up. And the problem is, some of them will be positive and some of them will be negative, and so they'll offset each other, and they'll kind of cancel each other out. All these that are above the line are going to be matched by some that are below the line, and it'll just say, well, you're close to the total, but you could be far off for everything. So there's a little trick we use. We square these so that the negatives, like if we're off by 3 in the negative direction, it becomes a +9. And if we're off by 3 in the positive direction, that's also a +9. So it's just the distance, not the negative or positive sign, that matters. And then we will just add up all these errors over all the points, and that becomes our criterion. We want to minimize the sum of squared errors, and that is naturally called least squares regression analysis, where you pick the intercept and slope so that the sum of the squared deviations between the data and the model, the green line, are as small as possible. And you say that's a good answer. And that's the one that the computer would calculate for you. So it's possible to have more than one x. So instead of a line, we might have something like a plane in 2 dimensions or 3 dimensions. But the principle is the same. We want to put that line or the plane as close to all the data points as possible. We find the sum of squared errors, and we minimize that by jiggling the intercept and slope until we get as small a number as possible. Now, we don't actually jiggle it. You can, those of you who remember your calculus class, you can use calculus, and particularly derivatives, to write an equation or a set of equations for what the intercept and slope should be to make this quantity as small as possible. We're not going to do the calculus here. This is already kind of mathy for most of our audience. But that's what's happening. We're finding the green line close to the black points by making all the little red stubs as small as possible, ignoring their signs. So that's the hidden mechanics inside the application. We'll finalize this talk by explaining the 3 different ways that we can use regression in a practical business problem.